Okay, so in this test, we want to show how we can just measure the flow coefficient through a weir. So we have like a structure here. This structure is called weir, and this one is called V-notch, and this one is a rectangular. So once we have like this kind of like a structure in a river or stream, the flow passes through this kind of like the structure and drops after this. So we have some formulation for that, but some of the coefficients or parameters in this kind of like the formula relationship between the head and the flow, we need to just determine through the experimental test or laboratory experiments. So this is like the features of the V-notch. So more specifically, we can just look at the V-notch feature items that we have in the laboratory. First of all, like the rectangular, the width is like the 30 millimeters, the height is 100 millimeters or 3 centimeters by 10 centimeters height. For the V-notch, we have two V-notches, one with a 30 degrees angle, and the other one is a 90 degrees angle. And the height of all of them are 100 millimeters. So let's see how we can just go for that formulation. I'm just going to quickly to the test and just give you the formula. You can see how we can just prove the formula in here in more detail or other reference books. Assuming that the width is shown by B for the rectangular notch, and for the V notch, the half of the angle, half of the opening, the angle of the opening is shown by theta, okay? And the height of the water above the bottom of the surface, bottom of the notch is shown by H, okay? So H is the height of the water from the bottom to the level of the water surface, okay? This is for example, this is the bottom of the notches, and this is the water level, and the height is denoted by H. So with that introduction, I can just directly give you the formula. The proof is given here. You can see here in this formula for the rectangular V-notch with the parameter B, this is the formula. The flow rate as a function of the width and a function of the H, which is the depth of the water above the bottom of the opening. Okay, so this is the H raised to the power 3 seconds or 1.5 times this coefficient. This coefficient has got the parameter CD times 2/3 square root 2g, and g, you know, is like the gravity acceleration, and CD is the parameter that the purpose of the test is going to determine this one. This is for rectangular one. For the V-notch, we have the formula to calculate the flow rate as a function of the height above the V-notch. But pay attention to this one. This one has got the CD coefficient of the V-notch. This is the one that the purpose of the test is to calculate this one. This is the ratio 8/15 square root 2g and times tangent theta, and theta is the half of the angle of the opening, and H is the height of the water above the bottom of the V-notch or the angle, and raised to the power 5 seconds or 2.5. Okay, so with that introduction, so let's see how we can just do this one. Normally, there are two methods to calculate that parameter CD, and to run the test, we can just either use the linearization of the formula or directly using the nonlinear formula. For example, we can write the formula in general format as a Q is equal to K times H raised to the power N. You know, if you look at the formula, compare this one, all the coefficient behind H is a variable and Q is another variable. It's independent variable, if you remember from mathematics, and this one is independent variable. And the whole things here from CD until B, all of them can be considered as a coefficient. So we can just all together consider as like a K, or the same in this formula from the CD until tangent theta. And the power, we can just denote it by N. in this relationship. Okay, so k is equal to that one, or n is equal to that one. It's fine. And once you take the log from both sides, on the left-hand side, we will have like q. On the right-hand side, if you remember from mathematics, we can have the log of the multiplications. We can write it as the sum, log k plus n times log h. And n, if you have something, the variable raised in a power, you can just convert it in a log as a coefficient, n, rather than from the power goes to the log that behind as a coefficient, n log h. Okay, so that's the relationship. Okay, so what's the difference? You can either use the measurement for h and q in the lab, okay, and then try to calculate k and n, or you can use again h and k, but use in this format. You know, you can just take this format, and this is like a linear equation. The difference between this and this, once you just plot it in a graph, this one is a nonlinear relationship because h and q, you know, looks like h, it looks like x, and q, it looks like y. Okay, so this is a nonlinear because raised to the power n, but here the power is 1. So if you remember from mathematics, this equation is called linear, and this one is nonlinear because the power or the order of the independent variable is not 1. So this is nonlinear and linear. In the past, specifically like let's say like 50 years ago, using the nonlinear equation was much easier to handle. But nowadays, with in the favor of the Microsoft Office Excel, for example, we can easily calculate everything nonlinear fitting curve. So this is like the next section is the fitting a curve once we plot the variations of the h and q. So if you just gonna, for example, for the linear one, if you plot log h against log q, you can have this one, and the gradient of this line is equal to n, remember, and the y-intercept, you know, this one is called y-intercept, or this axis intercept is equal to log k. You know, if you remember, this is a very simple from the mathematics. Linearization is like the line. So we have the dot. This, can you see this kind of like a crosses? This kind of crosses are the measurements that we can just calculate for h versus or against q, and we can plot that one, and we can fit a curve, and with the fit curve we can calculate the equation. This equation can be given to us in Microsoft Excel if you're just going to use that one, and once you're just going to have this one, you can easily calculate log q, or you can just take that from the formula and n as like a gradient of the line. Okay, so or the slope of a line. Okay, let's just look at like the more details about that. So I'm just gonna go to some examples in here. So for running the test, some important things is that we have like the tools to measure the height or the depth of the water above the bottom of the V-notch. Remember, these are like the tools that we have, but you need to just make sure you tangent this kind of like by using a steel or plastic rule perpendicular to the least kind of like the vertical ruler, and make sure that this one will touch the water surface. We'll practice these sort of things in the laboratory test to make sure you just exactly measure the water surface, not a little bit high or bottom, which has got some inaccuracies. And this is the ruler, the vertical ruler that you can use. You need to just tangent the tip of this kind of like the ruler. You know, there's a nailing part here, and you can just touch this one as a over the like the surface or water surface, and you can measure this one. You can either use this measurement, the bottom of this, or you can just use the top of that. Doesn't matter, but you need to stick to one place, either this one or this one for all readings. Okay. So once you're just gonna like, let's say we use this one, set this one all the time, and the first time before running the test, we just make sure that we just gonna read the water surface once it's just gonna touch the bottom of the kneeling, the bottom of the V-notch, and we can just set this at the datum. Once the flow is not running but is full behind the weir on the level of the bottom of the V notch. So we measure that one as like the datum, and then we run the test. We run the test with a number of the flows, for example. So this is the datum, the age is written and recorded here. And then later with the different like the flow rates, here you can see 3, 6, 9 measurements have been recorded here, and the corresponding age, by using the method that I said here above, you can just read the age and Q, or maybe more specifically, you can just record the gauge readings here, and then later, if you can take away this one from the reference, you can have the age, because reference is like the bottom of that, and this is the age that you can have it here. And the difference of that, you can see everything's here, and at the end, corresponding Q's is recorded here. If you want to use the linearization, you need to just take the log from like the both H and Q, okay, to write it here. And just bear in mind, if you're just gonna do that, you need to just use the metric units. This is H in millimeters, you need to just convert to the like the meters, okay? So we have like a log Q and log H, and then later you can, if you have like a log of the values, you can just plot them into the like the linear graph. You're just going to see here for different notches, like the V notch with the 30-degree opening. This is the line, or this is like the fitting a curve, and this is for rectangular. And for nonlinear, if you just use directly like the H and Q, you will have this kind of the curve, like the changes. And if you fit a curve, fitting a curve, by the way, is a very important like the aspects here. If you want to use a Microsoft Excel, we're just gonna use the curve fittings, like the facilities in Microsoft Excel. You can use the fitting curve in other software tools, but this is a very important aspects of the analysis here. So it's try to get used to using this kind of like the technique, curve fittings. So once you're just gonna get that one, you will get this kind of like the coefficient and the y-intercept, and then you can convert that one to a coefficient and the power here. And then by equating this value with the original coefficient, you can easily calculate the CD. Okay, that's the CD for example, this test, the rectangular one. And for the V notch, the same. You're just going to do the same as this one, and you can easily calculate the CD in this formula for the V notch as well. So we just and you can see here. And then you need to just discuss about the agreement between the to what extent the experimental results agree with the theoretical value. For example, how much we are close to like this power, because this power for the V notch is like the 2.5, and for the rectangular is 1.5. We need to just make sure if we just get to this value as much as possible or not, and if not, we need to justify what's the reason and what's the level of inaccuracy. So that is the V notch and the weir over the flow. Thank you.